And we are live. Hi, and welcome to the stream, kind of. The reason I'm doing this as a live stream and not really broadcasting the fact that I'm doing it is it's just the fastest way for me to upload a video to YouTube, honestly, because as I learned last week, if I record a video and then wait for it to upload over my slow internet connection, it would take forever. If I just live stream, it's already uploaded. So it's the fastest way to do it, and I have to apologize right off the bat. I have to make this quick because my wife just called me and said that she had a flat tire when she was at the grocery store. So now we have to go figure that out. So I have to make this kind of quick and then I'll be on my way. But I did want to record a message and say, first of all, hello, and say we've heard the news, obviously, and I'm very sad over it, as I'm sure you guys are too. Maybe, probably. I think you probably are. I don't have like a speech prepared or anything like that. Okay, these are my notes from today, so this is just, I'm not going to be able to really say anything eloquent or nice or anything like that, but I guess I wanted to say that, you know, we never really got our proper end of the year goodbyes. It's really strange to try and do this just looking into a camera and not being there in person with you guys, but I wanted to say that I will miss you guys a lot. You have been a wonderful class. I've really enjoyed being your teacher this year, and I really appreciate all the hard work that you guys have done. I appreciate how you have made the class fun, and it's been a good run, and I'm going to miss you guys a lot. To my seniors, good luck on your next step. Please don't hesitate to come back and visit. Send an email anytime, anything that you need. You know, I have total faith that you guys are going to go out there and you're just going to do great in college, or wherever you're going to go. And yeah, I miss you guys. I don't really have anything else to say other than that without getting too dramatic, but I did want to also mention one thing. You guys, you never really know how strong you are until you are put to the test. And so in a time where you are being pushed and you are being tested, you can find your true strength if you allow yourself to put the effort out there. You are tough, you are strong, and you got this. You can do this. You're smarter than you think you are if you just put the effort there and do it. So put the effort there. You guys got this. If you know anyone who is suffering through this disease, my heart is just there, and I'm not a very religious person or anything like that, but I'm praying to someone. If you need anything at all, do not hesitate to reach out to me or to anyone at Fenton. We are all here for you, and help is just a quick email away. So please don't hesitate. And as we kind of move on then, I wanted to take like 5 minutes and talk about the next concept in magnetism. I know it's so hard to transition from something like that, and I really have to like wrap this up pretty quick because of the whole flat tire situation. But here we are. So last week we talked about how we can have a magnetic field created by a current carrying wire. So if we have a wire that's carrying electric current, so imagine there's some electric current going through that wire, then it will create a magnetic field. I don't really love the way I drew that just now. Here, wait, I'll make up for it. Well, that's not the worst thing I've ever done. Anyway, it will create a magnetic field, and the direction that that particular magnetic field is going is a little tricky. We'll talk about it later this week we will do either Tuesday or Wednesday we'll do a live Zoom. I couldn't do a Zoom today because even before the flat tire incident, my daughter has been kind of having a cranky day. So, but Tuesday or Wednesday we'll do a Zoom and we'll talk about it more. The direction of the magnetic field is a little tricky. You have to use this thing called the right-hand rule. There's actually 2 right-hand rules, and it's going to be a little bit more time-consuming to explain, so we're not going to go there today. But we do know the magnitude of that magnetic field from last week is mu naught I divided by 2 pi r. Review last week's video if you need any help with understanding what that means. Now, what we're going to do today is talk about one of the most important inventions in all of human history, the solenoid. If you want to know what they're used for, Google it. But if we take this current carrying wire and we start to bend it into a bunch of loops, so it's going to end up looking something like this. This creates an extremely strong magnetic field inside the solenoid. So we've got our current going through the wire and looping around. That's the direction of our current. It creates this extremely strong magnetic field inside the loops themselves. So these magnetic field lines come inside the loops themselves. So they're going like through the middle of this. It's so much easier to explain when I can show it to you in real life, but the magnetic field lines are going through the middle of these loops. I have an actual animation from a more professionally made website that I'll show you guys in a second, and it's very, very strong magnetic field, which can be useful for a lot of applications, like starting an engine, so like starting your car or something like that uses a solenoid. Lots of really powerful applications. By the way, the magnetic field lines still follow the rules. They form closed loops, but the magnetic field outside of the solenoid is very weak. It's a very weak magnetic field outside of the solenoid, so we ignore it. It's inside the solenoid where the magnetic field is very strong, and the formula for it is not too complex. There's just a couple of things that are a little tricky on there. So to calculate it, the magnetic field inside the solenoid, outside the solenoid it's practically 0. But inside the solenoid we're going to take that same permissibility of free space, that 4 pi times 10 to the negative 7th, we're going to multiply it by a new constant k, which is basically what is in the core. What did you take that wire and wrap it around? Did you wrap it around something like a marker, or did you wrap it around a piece of iron? So, or did you wrap it around air? If you wrapped it around air, K is about equal to about 1. If you wrapped it around a piece of iron or something magnetic, think about it. That magnetic core is going to strengthen the magnetic field even further. So K becomes something like 300. So it's a multiplier that increases the strength of the magnetic field if you wrapped your wire around something that is magnetic, like iron. Multiplied by the turn density, I'll explain that in a second, multiplied by the current. So let me explain what all those constants are, and then I have to be on my way. And what I'm going to do is I'll have an assignment posted, and I'll explain what the assignment is in the instructions on Google Classroom. But we know that B is magnetic field. We know mu naught is the permissibility, I don't even know how to pronounce it or spell it. Let me show it to you. Boom. We should be there now. And permeability. Why did I think it was permissibility? I don't know. Permeability. I got that right last time. How permeable, how easy is it for a magnetic field to move through the material that you're moving it through? So, yeah, good enough. So permeable, I can't even spell it. Permeability. You know what? We got better fish to fry. We got a flat tire we got to go fix. Anyway, that's always just 4 pi times 10 to the negative 7th. K is the relative permeability based on the material that you're wrapping the wire around. So if it's in a problem, if it's not given, just make it equal to 1. If it's just like not told, if you're not told what K is in the question, just make it 1. But if it's something like an iron core, like I said, it can be like 300. So multiply it. The turn density. How tightly coiled is your solenoid? So the number of turns, or loops if you want to consider it like that, divided by the length. Divided by the length of the solenoid. So that's like a density thing where how many loops per meter do you have? So like how many loops per meter? Well, if you wrap it really, really, really tightly, this number is going to be bigger, stronger magnetic field. If you wrap it really, really, really loosely, this number is going to be smaller, and therefore you have a weaker magnetic field. And then finally, the last bit of the equation is the current. In amps, I don't need to say anything more about that. So there's going to be a video on, no, this is the video. There's going to be an assignment on Google Class that talks about this stuff. I've got to run. We will do a live Zoom Tuesday or Wednesday, and I will talk to you guys. Thank you for watching, and I'll talk to you soon. Goodbye.